Dear students of the structural design course, I received a lot of requests concerning the solutions of the written exam of the 15th of January. That is why I decided to record this video in order to show you how the assignment was to be solved. I will also focus on the first question, which was rather theoretical on reinforced concrete members. So we'll now share my open board. You may all remember what it looked like, the exam, but I will go through the text quickly. So the first question read, describe concrete as a building material by outlining the main mechanical properties relevant for structural design. Outline the fundamental assumptions concerning the design and check of reinforced concrete sections consisting of concrete plus steel rebars, with particular attention to the problem of cracking. Sketch some examples of reinforced concrete beam section, shape and reinforcement, clearly explaining the role of the different components. Now, if you go back to the class which was given on the 10th of December, basically this is what I wrote, what I projected during the class. So, introducing concrete and reinforced concrete members, which are the ones commonly used in practice, I focused on the fact that this material is originally in a fresh state, which means it's workable. So this was one main property which was to be outlined. Therefore, being workable, it has a great flexibility as regards the shape of the structural members. So basically you are free in comparison to steel, where you are in a certain sense restrained to adopt the sections that are available on the market and that are typically produced in industry. I mentioned the fact that concrete can be cast in place or it can be prefabricated by outlining, and this is why I highlighted the first part of this item, that we were going to focus on cast in place reinforced concrete members. An important thing to underline about concrete was the fact that it's a heterogeneous material, which means it consists of different ingredients. It's a composite material, and these ingredients are important to know. So cement, which plays the role of binder, so it's like the glue that keeps together all the components of concrete. Then there are aggregates, basically natural stones. They are usually subdivided depending on their dimensions. So we have gravel, which is typically between 4 and 16 millimeters, and sand, which is between 0 and 4 millimeters. Now, these, of course, are numbers I gave, also the proportions, so 300 kilograms per cubic meter and 1900 kilograms per cubic meter. These were figures I gave to just give you an idea, to let you taste a little bit what concrete is about. But of course, it was not mandatory to remember these figures by heart. And then, of course, there is water, which is given typically in quantity which is liters over cubic meters, so ranging between typically 150, 180 liters per cubic meter. This is basically what we call concrete, so it's important, especially for the people who speak Italian, to know the difference between cement, which is cemento, and concrete, which is calcestruzzo. So strictly speaking, accurately speaking, cement is just an ingredient of concrete, whereas usually we also typically say calcestruzzo armato or cemento armato, meaning the same thing, so basically reinforced concrete. Then of course hydration should be mentioned, so the fact that there is a complex set of phenomena which take place that represent chemical reactions between the ingredients that make up concrete and that lead to the development of mechanical properties, so that bring in the hardening of concrete, which is then typically used as regards structural applications in its hardened state. What about the mechanical properties? Clearly, there was a big focus on compressive strength, which is measured in megapascals, so Newton over square millimeters. Many of you had problems with the conversion of units of measure, but if you look here, it's clearly said that megapascal is Newton over square millimeter. So we have cubic specimens with their dimensions, the typical failure pattern and the way the concrete compressive strength is measured on cubes. Typical values of compressive strength, again, to give you an idea, to make, for example, the comparison with steel, whose yield strength is something around, I mean, the one we saw in the first part is typically something around 250 megapascals or so. And then the density, of course. So for normal concrete, we have a density which is in the order of 2,300 kilograms per cubic meter. Then I focused on the fact that if you are interested in the structural behavior of concrete, a more objective way to look at the properties of concrete and specifically on the compressive strength is to measure it on cylinders, because cylinders tend to be less sensitive than cubes to the problem of friction, and therefore the measure of compressive strength on cubes is not fully objective. This fact is reflected by the observation that when you measure the compressive strength on cylinders, it is systematically lower than the compressive strength measured on cubes if, of course, you measure it on nominally identical specimens as regards the mixed design. So if you have a mixed design, a given mix of the concrete ingredients, and you cast cubes and you cast cylinders, and then you measure the compressive strength, you typically have different values, and the difference is cylinder compressive strength measured on cylinders is lower than the compressive strength measured on cubes, okay? Then why, this is a typical question I asked during the oral examinations, why do we cast cubes? Well, given that there is a relation, which is this one, between the compressive strength measured on cylinders and the one measured on cubes, testing cubes or testing cylinders is the same. The relation is linear. You simply have to do a conversion by multiplying by this factor, which is 0.83, okay? But cubes are more easily done when you are on a working site, and moreover, they don't need to be reworked when they are tested in the lab, because the faces, the lateral faces of the cube are plane, whereas the only plane faces of the cylinder are the end faces, which needs, in any case, some additional working, like grinding, because it's, of course, surfaces that are not perfectly plane. Then we talked about the role of duration of the load on concrete, and we simply said that the longer the duration, the lower the compressive strength, which tends to a limit, which is a long duration compressive strength, which is 15% less than the instantaneous compressive strength we measure in usual tests. I said that a typical test on a concrete cylinder lasts something like 1 minute, okay? Just to give an order of idea, that's probably a little more. Yes, here I wrote 2 minutes. So this is an instantaneous test. But if you consider the role of the duration, the resistance, the compressive strength you measure is lower. Clearly, this is relevant when you do structural design, but you cannot do laboratory tests that last like 1 hour or 1 day. It's time consuming, and time, sorry to put it in this way, time is money. So we typically do instantaneous tests, but when we do the calculations, we have to take into account the role of load duration, okay? And then, of course, there was the big issue about the behavior in tension. Just to mention that if you test a cylinder in tension, you get a value of tensile strength, which is definitely lower than compressive strength. And this is a basic feature of concrete. So concrete is a strongly non-symmetric material, with the tensile strength being approximately 1/10 of the compressive strength. This means that if you were to subject a concrete member to a load, if you think about the typical distribution of stresses in the elastic state, either you have to limit your working stress below the tensile strength of concrete, but this, I said, is not advantageous from the economic point of view, because you would have to choose bigger sizes just to make up with the low tensile strength. If, on the contrary, you go beyond the tensile strength of concrete, you will get cracking, and typically cracking in the areas that are subjected to be, that are supposed to be subjected to tension. So this is the importance of the role of the structural analysis. So The idea, which I clearly explained in this slide, is that when you have reinforced concrete, you use steel and concrete together in such a way to overcome the weakness of concrete. So where concrete is in compression, it can sustain the applied loads without major problems, whereas where it is in tension, it needs some reinforcement, some steel reinforcement, which can bridge the tension and the tensile stresses that takes place because of the application of the loads, okay? So these were the basic ideas. Then, of course, I also asked you to sketch some reinforced concrete sections shapes. And this is, for example, explained here where there is this concrete section. The second question of the exam was a practical application of steel design. So here you see the structure that was to be designed, and the text said, consider the structure in the figure below consisting of a beam. So we are thinking about, I was thinking about the horizontal member, and it was also written beam, supported by a tie, and the tie is the vertical member. Here it was also clarified that the beam section was an IB section, whereas the section of the tie was a circle, okay, of diameter d, small d, okay? So how was this exercise to be solved? The first part of the question was, perform the structural analysis of the beam by plotting the diagrams of the internal forces, shear and bending moment as a function of P and L, okay? So first task is basically to design this member, this horizontal member. And then there was a point B that said, determine the tension force in the tie as a function of P and L. So how was this to be done? There were certain clues given in the text. So we know that the beam is subjected only to shear and bending. And by asking for the tension force in the tie, I'm kind of suggesting that there is no other internal action in the tie other than the tension force. As a matter of fact, if you look at the tie, you clearly see that being a steel member, it fulfills the 3 golden rules in order to be subjected only to an actual force. Namely, at the boundary you have hinges, the member is straight, there are no loads applied at the inner of the structural member. So definitely this is a truss, and looking at how the structure is as regards geometry, it is plain to see that the beam is suspended to this member, and therefore we expect to have tension in the tie. So how was this to be solved? We have the beam. So the beam is basically horizontal member with a distributed load. Okay, so we'll reproduce it here at the bottom. Small arrows to indicate the direction of the distributed load. And at the boundaries, we have a hinge at the first end. So there is clearly a reaction force, which is vertical. And starting off in a very accurate way, we could also mark a horizontal force, okay? We call them VA and HA, okay? Then, of course, we have a hinge also at the other end. It doesn't matter that this hinge is an internal hinge, so it's a hinge that is between 2 members of the structure. Still, since it prevents 2 components of these two displacement components, vertical displacement and horizontal displacement, a priori, we have to mark two forces, and we call them VB and HB. Okay? Clearly the load is P. Now, as regards rigid body equilibrium, we can concentrate the load at the midspan, where there is the line of action of its resultant. And we can write here the resultant force, which is clearly P, so the value of the distributed load multiplied by the length, which is L. And by means of this set of loads, we can write equilibrium equations. What are the equilibrium equations? The equilibrium equations are horizontal equilibrium, Rx equal to 0, which immediately leads, considering that my horizontal forces HA are directed, HA is directed towards the right and HB is directed towards the left, Rx is simply HA minus HB equal 0. So the result is clearly HA equal to HB. As regards Ry, we know, as it is usually the case, that the sum of the two vertical forces, VA and VB, which are directed upwards, must be equal to the applied load, which is directed downwards. So in equation, VA plus VB minus PL equal 0, which immediately leads to VA plus VB equal to PL. Then we need a rotation equilibrium. So a rotation equilibrium is, for example, MA equal to 0. So if there is a hinge at the first end, the moment of the forces with respect to this point should be equal to 0. What we have is no contribution by HA and HB, whose line of action intersects point A. No contribution by VA for the same reason. The only contributions are by PL, whose lever arm with respect to A is L divided by 2. So the distance normal to force PL with respect to point A is L divided by 2. So the contribution is PL multiplied by L divided by 2. And then we have minus VB equal to 0. And this immediately yields VB equal to PL divided by 2. And then, of course, taking advantage of the second equation, so the vertical equilibrium, we have VA equal to PL minus VB, and this is equal to PL divided by 2. So the two vertical reactions are equal. They are directed upwards, as I mark them here, and their value is typically PL divided by 2, PL divided by 2. As regards the horizontal forces, you see that from considering only the beam, we cannot determine the value of the horizontal force. We only know that the two forces, HA and HB, marked in this way, have to be equal. So they have to be one the opposite of the other in order to guarantee that there is equilibrium in the horizontal direction. What we then have to solve is the vertical member, which means the tie. One could start and say, okay, here there is HB. For the principle of action and reaction, if the force HB is directed towards the left on the beam, it is directed towards the right on the tie, okay? And then we have VB, and clearly, since VB is directed upwards on the beam, it has to be directed downwards on the tie. In this case, it makes no sense to mark again symbol VB, because we know the value already, and the value is PL divided by 2. So it's a tension, because you see it's directed downwards at this end, so this represents a tension, and this tension is clearly equilibrated by a tension force which is applied at the top. So as regards vertical equilibrium, I'm not writing the equation because it's very simple. You have PL divided by 2 at the bottom, PL divided by 2 at the top, and this representation clearly highlights the fact that the tie is in tension. as should have been expected, because we said it from the beginning, it's tension member. So basically, the answer to point B was, what is the tension force in the tie? The tension force in the tie is PL divided by 2. Okay? What about the rotation equilibrium? Now, having mentioned the fact that since this is a truss, okay, there are no other forces than the actual force, I could immediately delete HB, but let's see why HB is 0, just to brush up a little bit on basic concepts we mentioned during the classes. So if you have HB at the bottom, you should have HB at the top in order to guarantee translation equilibrium in the horizontal direction. But then again, if I write the equilibrium with respect to the point at the top, what is the result? The result is that there are no contribution by this PL divided by 2 force and by this HB force at the top. The only contribution is by HB at the bottom, because also PL divided by 2 gives no contribution. So the rotation equilibrium immediately gives you HB times the length of the tie, whatever it is. It is not even given because it's not relevant for the result. And what you get from this equation is having the tie a predefined length, so H is definitely different from 0, HB equal to 0. And by knowing that HB is equal to 0, we know HA is equal to 0. Okay? So, concluding this, HA is equal to 0. Of course, to conclude this exercise, you also have to sketch the diagrams of the internal forces, but as you see, this is basically a simply supported beam. So the bending moment and shear diagrams are very easy to determine. I will just plot them because we have seen them a lot of times during the classes in one way or the other. So the shear force can be represented by assuming a positive direction, a positive convention with the shear clockwise, and the diagram is simply, this is the beam. So at one end you have a positive shear, which is PL divided by 2. At the other end you have a negative shear, whose value is PL divided by 2. And the diagram is this. As it always happens in beams where there is a distributed load, the shear diagram is a straight line. Values which should be specified are PL divided by 2 minus PL divided by 2. Here you put a plus and here you put the minus. This is a diagram which gives all the information I need in order to know whether you got it right. Then there is a bending moment. For the bending moment, since I gave you full freedom to decide your own convention, you have to specify what convention you use. Now, my convention, the Italian one, is to plot the bending moment diagram on the tension side. Simple equilibrium equations written on portions of the beam will clarify that the bending moment is always positive. The trend is parabolic. Why parabolic? Because you have a distributed load. So you get something which is like this. I hope I can get the parabola right, more or less. Better the second part than the first part. Now clearly, being 0, the bending moment at the first end and at the second end, the important thing to know is the maximum value, and in a simply supported beam, as it is always the case, it's PL squared divided by 8. Then there was point C, and point C of the problem was design the section of the beam assuming an IP profile by limiting the maximum displacement at midspan to Vmax equal to L divided by 300. Modulus of elasticity of the steel is equal to 200 gigapascals. So basically, you have to make sure that the beam is designed in such a way that the maximum displacement at midspan represented in this diagram, so the deformed shape under a distributed load looks something like this with a maximum displacement at midspan, and the expression is given by this. so function of the load, the length, the elastic modulus, and the second order moment of area of the section, does not exceed L divided by 300. How much is L divided by 300? So the data of the problem were, it was written just before, P equal to 15 kilonewton over meter, and L equal to 6 meters. Immediately, if you do your calculation, the limit displacement, which is equal to L divided by 300, is equal to 6 meters are 600 centimeters divided by 300, this is 2 centimeters. Or if you prefer, in meters, 0.02 meters. How do you design the beam? So you have to basically make sure that Vmax, which is given by this formula, so 5PL4 divided by 384 E times J, is lower or equal to Vlim, the limit value of the displacement. Look at this equation. There are known quantities, P, L, E. There is just one unknown quantity, J. So as we showed during the classes, you can reverse this equation. And this condition is simply expressed by the fact that J, the second order moment of area, is greater or equal to 5PL4 divided by 384 E multiplied by V limit. I also showed you an alternative way of using this formula, whereby you consider this condition, which is typically expressed with the limit displacement as L divided by a quantity alpha. So if alpha is equal to 300, basically you can express this same condition as 5PL to the power of 3 multiplied by alpha divided by 384 E. Okay? To the numbers, what are the numbers? So here you have to use the units of measure which are given here, or you can convert them by suitable operations, which are basically converting the units of measure. So we have 5. P is given in kilonewton over meter. Now, since kilonewtons are basically 1,000 newtons and meters are 1,000 millimeters, this load is equivalent to 15 Newton over millimeter. So I use it as such without changing it. Then we have L, which is expressed in meters. So in order to change it to millimeters, I multiply it by 1,000. So 6 meters are 6,000 millimeters. And this is L to the power of 3. Multiplied by alpha, which in our case is, as specified, 300. Then, under the sign of fraction, we have 384 multiplied by E. Now, E, the text said, is 200 gigapascals. So, E equal to 200 gigapascals. Knowing that, as specified previously when I showed you how you were supposed to, what you were supposed to write as regards question 1, since we know that megapascals are Newton over square millimeter, it is convenient to convert this number in Newton over square millimeter, so megapascals. The relation between a giga and a mega is giga is 1000 mega. So what you have here is an elastic modulus, which is 200,000 megapascals. This, since all the units were converted into Newton and millimeter, will give you a second order moment of area, which is in millimeter to the power of 4. In the table where we have to pick the correct profile, the second order moment of area is expressed in centimeters to the power of 4, which means basically that when we get the result, sorry, I didn't want to write equal. In order to have centimeters to the power of 4, we have to divide by the ratio between centimeters to the power of 4 and millimeters to the power of 4. Clearly, since between a centimeter and a millimeter there is a ratio of 1 centimeter is 10 millimeters, then 1 centimeter to the power of 4 is basically 10,000 millimeters to the power of 4. So in order to get a result which is consistent, you have to divide by 10,000. And you will get the result which is exactly in centimeters to the power of 4. Doing the calculation, which I will redo, 5 times 15 multiplied by 6,000 to the power of 3 multiplied by 300 will give you a very high number, but then you can divide it by 384 multiplied by 200,000. And everything is to be divided by 10,000. Final result is 6328. So you get a minimum second order moment of area, which is 6328 square centimeters to the power of 4. This is the minimum, but we are obliged to stick to the table, which gave you the second order moment of area for commercially available IPE profiles. Clearly, this is the minimum, so all the profiles which have a second order moment of area which is smaller than this one are not okay. You have to pick the first that has a second order moment of area which is larger than this one, and you can see it's IPE 300. So this is your choice. Your choice is to stick or to respect this limit of displacement. Your choice is IPE 300. And from now on, everything has to be done assuming that the beam consists of an IPE 300 profile. Point D. Check whether the section subjected to the maximum bending moment is in the elastic range, which means maximum stress lower than 160 megapascals under the given load. Let's quickly go back. We know that the section with the maximum bending moment is midspan. The maximum value of the bending moment is PL squared divided by 8. And therefore, we have to calculate the maximum bending moment. So this is, as I said, it's point D of the assignment. The maximum bending moment is PL squared divided by 8, whose value becomes, with the given data, so 15 kilonewton meter multiplied by 6 meters to the power of 2 divided by 8. I will redo the math. I know the value by heart because I read all your written exams, but I will recalculate it. It's 67.5. Units of measure, so this is a kilonewton over meter. These are meters to the power of 2. So unit of measure is kilonewton per meter. How do I calculate the maximum stress? This is something we've seen in class. Assuming an elastic distribution, you have to simply divide the maximum bending moment, which I just calculated, by the section modulus for the elastic range. So VXEL, as it is called, VELY, as it is called in this table. So WELI is expressed in cubic centimeters. The value for the selected profile is, you can read it here, 557.1. Sorry, so I will correct this. The correct name is WL, Y. So basically I have to do 67.5 divided by 557.1, but I have to be careful once again about the units of measure, because this is kilonewton times meter, and this is centimeters to the power of 4. The limit stress, as I mentioned previously, is given as megapascals. So it is convenient once again to transform everything in Newton millimeters. Since we have kilonewtons, which are 1,000 newtons, and meters, which are 1,000 millimeters, this bending moment expressed in Newton times millimeter is 67.5 multiplied by 10 to the power of 6, which is the same as writing 1 million, but in this way it's a more compact writing. Again, how do I convert this? Sorry, here I wrote something which is wrong. This is not to the power of 4, this is to the power of 3, as we just said. Again, this is in cubic centimeters. How do I transform it into cubic millimeters? Simply 557.1 times 1,000, which is 10 to the power of 3. Basically, 10 to the power of 6 divided by 10 to the power of 3 gives 10 to the power of 3. So my final calculation that I have to do is 67,500, so basically 67.5 multiplied by 1,000 divided by 557.1 equal to calculation . The result is approximately 121 megapascals. So the answer to the question of point D, check whether the section subjected to the maximum bending moment is in the elastic range. Since this value is lower than the given stress, limit stress, which is 160 megapascals, the answer to the question was, okay, it is in the elastic range. For point E, the question was different because the load was changed. So the load was bigger, 22.5 kilonewton over meter, specifying that we are working at the ultimate limit state with a maximum design yield strength, which is 220 megapascals. The question of point E was, check the section of the beam designed previously at the ultimate limit state, which means we now have to assume not an elastic distribution, but a plastic distribution, as was explained during the class where we focused on the behavior from the serviceability limit state to the ultimate limit state. And how do we do it? We have to calculate the resisting plastic moment the section can develop upon full plastification, which is simply given by FYD multiplied by the plastic section modulus, which is called, following the table, WPL, Y. So the calculation is 220 multiplied by, let's look in the table, what is the plastic section modulus for IPE 300, 628.4. So here we put 628.4, but in order to be consistent, I want to transform this quantity in millimeters to the power of 3, so cubic millimeters. So once again, I have to multiply by 1,000. In this way, I am consistent because here I have a stress which is expressed in megapascals, so Newton over square millimeters, and I multiply it by a quantity which is cubic millimeters. The result I will get, which is a bending moment, will be expressed in Newton times millimeter. I get, let me do the calculation, 220 times 628.4 times 1,000. Result is 138,248,248,000 Newton per millimeter. In order to convert it into kilonewton times meter, doing the opposite of what I did previously, I have to divide by 1 million. So the final result is 138.24 or 25, let us say, kilonewton meter. How do I check the section at the ultimate limit state? I simply have to check that this, which is a resistance of the beam, the maximum bending moment the beam can sustain upon full plastification. So this has to be larger than the applied bending moment, which we usually call MSD or MED. How much is MSD? Back to the internal force diagram, PL squared divided by 8. It's not changed, the distribution and the maximum value. What is changed is just the load, because as we said many, many times, from serviceability limit states to the ultimate limit states, there is an increase of load, hopefully. So here it's PL squared divided by 8, whose value is 22.5, multiplied by 6 to the power of 2, divided by 8. Calculator. $101.25. Does this sign hold? So is this larger than this? Yes. And then the answer is okay. Finally, point F. At the ultimate limit state, we have to design the section of the tie. So section of the tie, which is in tension, is not designed on the basis of some displacement requirements, on some deformation requirements. It is designed on the basis of strength, on the basis of maximum bearing capacity. How do you design the tie? Well, you have to remember that the resisting force that can be developed by a tension member developing its full plastic capacity is simply Fyd multiplied by the area. I know Fyd. I want NPLRD to be larger than NSD. By reversing this equation, I can determine the minimum area the tension tie has to have in order to fulfill this check. Let me create a little bit more space. So let me just bring up this equation. First, let us calculate NSD. What is NSD? Back to the structural analysis part. We know that the tension force of the tie is P, the load, multiplied by the length divided by 2. In the case of this check, which is to be done at the ultimate limit states, so with this value of load, this value of the tension force is 22.5 multiplied by 6 divided by 2. 67.5 kilonewtons, because it's a force. The fact that this value is equal to the value of the maximum bending moment is a mere coincidence, okay? Mere coincidence. What is the minimum area? Minimum area is equal to what? 67.5 kilonewtons, which I directly translate into newtons by multiplying by 1,000, okay? And then I divide by Fyd, which is 220 megapascals. Minimum area, if I write the equation in this way, is expressed in millimeter, and the value is 306 square millimeters. Of course, it's an area. Now, the exercise or the assignment asked you to design the section of the die assuming a circular section with an even diameter. So I wrote 10, 12, 14. What is the diameter corresponding to this? What is the diameter corresponding to this area? The diameter corresponding to this area can be determined by remembering that the area of a circle is simply P, Greek P, multiplied by the diameter to the power of 2 divided by 4, which means basically that the minimum diameter is equal to what? To the square root of 4a minimum divided by P. Let's do the math. So the math is 4 times 306 divided by P. The value under the square root is 389. So if I do the square root of 389, I get 19.7 millimeters. Which means if I have to choose a diameter which is even, I have to choose the first even diameter that is larger than 19.7 millimeters. So the result was 20 millimeters. Okay, some of you have tried out, did the opposite, so they checked the die with 10, 12, 14, 16, 18. This was another way to do it, clearly more time consuming, still valid, of course, because it brings you to the result. Clearly in this case, since it's so simple, you could have done it in this way, which was more direct. Okay, it took me 47 minutes to do everything, also explaining all the passages I did. This tells you that I think it was not so complicated to do everything in 3 hours. I'm not saying, of course, that when I was your age, I would have done this in 47 minutes. But I think if you look and you go through the calculations, they were very simple, especially if you look at the fact that all the relevant equations for the checks, this one, and this one were very, very straightforward in the sense there were no coefficients to be remembered, just the maximum bending moment and this quantity and so on for the other points. That's it. I hope you enjoyed this sort of tutorial, and get back to me if you have further questions about this written exam, and see you soon.